spaces. For example, a call from an application to the BSD server. Unfortunately, it's pretty complicated to use Mark IPC for RPC. And that's what the Mark Interface Generator, or short MIG, is for. MIG simplifies RPC. For example, if main wants to call func, which is in another address space, MIG generates func in the first task, which looks exactly like func in the second task, but it just combines the arguments into a message and sends it to the other task. The other task then receives the message, decodes it, and calls the local func. The return value will be sent in an analog way. So, effectively, a function in task 1 just call a function in task 2. The blue code is generated by MIG from an interface definition file. Now, let's look at how BSD interacts with Mark. Like we said, Mark consists of the components memory manager, scheduler, and the interrupt or execution handler for low-level hardware management. These components use the concepts of Mark task, Mark thread, Mark exceptions, and Mark message. Then, BSD sits right on top of these concepts and extends a Mark task into a BSD process by adding context like the command line, a working directory, and so on, as well as extending a Mark thread into a POSIX thread, and it also converts Mark exceptions into BSD signals. BSD also adds extra components like the virtual file system, BSD sockets implementation, and the /dev infrastructure. On top of all this, there's a syscall interface. It exports the syscall interface, exports standard Unix syscall functions like open and fork to userland. Oh, sorry. What is wrong with that? Is there okay. Mark Message API gets exported to user and directory. So there are basically two syscall interfaces, one to BSD and one to Mark. The syscall handler distinguishes between those by looking at the syscall number. And positive numbers get routed to BSD because these numbers are compatible with the standard syscall numbering of BSD, and negative numbers call into the Mark APIs. Applications should never make syscalls directly, but always go through libc, because Apple doesn't guarantee a stable syscall interface. And this is the reason why Mac OS X does not allow static binaries, that is, executables that contain a copy of libc in their binary. Such a static binary might not work on later versions of Mac OS if the syscall interfaces change, of course. The third component of Axon uses the I/O kit, which is the driver infrastructure. I'll first demonstrate how driver development traditionally works on systems like Windows or Linux. If you want to create a new driver, you usually take the closest match, you duplicate the C file, and you make the respective changes to the new file. This creates a lot of duplicate code, and it will always duplicate the bugs too. And it makes overall maintainability harder. A simple solution, or rather workaround for this, is to unify the C files and mark the differences with if-def or if-tests at runtime. Obviously, neither solution is very readable, and runtime ifs even have a performance impact. So this is how the I/O kit does it. It solves the problem by using object orientation and a subset of C++ programming language. A generic driver is then used as a base class, and a more specific driver inherits all the code from this class and overrides all the functions that need a different implementation. The I/O kit offers many more and powerful modern features, but I'm not a driver person, so let's move on to the KEXT. I/O kit drivers are a special form of KEXT, which are kernel extensions. A KEXT is practically anything that loads into the kernel at runtime. It's just like the Linux kernel modules. And KEXT can also contain a file system driver or network protocols, or just provide random functionality if the kernel provides the necessary interface to hook into. This is a picture of some KEXTs that are stored in system library extensions, like, for example, as you can see, the Apple iSight KEXT, or Apple ABD keyboard KEXT, or Apple AirPod KEXT, and so on. This is the MS-DOS file system KEXT, which is the FAT file system driver. As you can see, a KEXT isn't just a simple file, but it's actually a directory that contains, next to the actual binary, a few other files, like, for example, the info plist. This file, just like the others, contains meta information about the KEXT, like the versions of the application binary interface of the XNU components that it requires. This example requires at least 8 of BSD, version 8 of BSD, Mark, and unsupported, and version 9 of libkern. Libkern is another small component of XNU that provides various utility functions like C++ base objects, data types, or atomic functions. And unsupported puts together all functions for which Apple doesn't guarantee compatibility in future versions of macOS. That's why it's called unsupported. Now, let's move on to booting. Booting of macOS is very different to booting a PC. So let's look at that first. On a PC, booting works through the firmware called BIOS, the basic input-output system, which is an ancient 16K bit firmware that can only address 1 meg of memory, which you can see on the right side. The only thing that BIOS does is read the first sector, the master boot record, into the lower 30K of RAM and jumps to it. So the BIOS does not know about partitions, partition types, or file systems. So the boot sector is completely on its own to find partitions and the files inside the file system that are required for booting. Booting on Mac is quite different. The Intel Mac firmware is called EFI, the Extensible Firmware Interface, whereas PowerPC-based Macs used open firmware. It's a different system, but it has basically the same set of features. In contrast to BIOS, EFI is 32-bit code, and it understands the EFI partitioning scheme called GPT. It also understands the old Apple Partition Mac, APM, used on PowerPC Macs, and it can read HFS. It detects which partitions are bootable by actually looking into the file system. If you hold down the Option key while turning on a Mac, EFI will present a boot picker, which shows all bootable partitions connected to the machine. EFI then reads the bootloader file from the selected boot file system and executes it. The driver kernel extensions, the KEXT, like I just said, are loaded by going through all the objects in system library extensions, and they're matched against the detected hardware. In case neither the kernel, nor the hardware, nor the set of drivers on disk has changed since the last boot, the kernel cache gets loaded instead, which is the kernel and a set of necessary KEXTs that were pre-linked into a flat image. It's also interesting to know that the kernel file is called Mark kernel, but of course it's XNU and not Mark. If you look at the file type of an executable like this kernel file or a library, you will see that instead of virtually every other Unix-like system, Mac OS X does not use ELF, but Mach-O. For example, the lib system is a 4-way universal Mach-O file, which means it contains code for all 4 supported architectures. One advantage of that is that no separate directories for 32 and 64-bit libraries are needed, as on Linux or on Windows. And this goes even further. Every single file, every single binary on a Leopard disk, even the kernel, runs on PowerPC and Intel. So the same hard disk can be used to boot computers with totally incompatible CPU architectures. The kernel function, grade binary, is responsible for choosing the most suitable binary image in one Mach-O file. So if on a 64-bit system there's a 32-bit and a 64-bit part in the file, it'll choose 64-bit, of course. And on an Intel system, it will choose Intel over PowerPC. But if there's only a PowerPC image on an Intel system, it will choose this one and invoke Rosetta. Rosetta is a compatibility solution which is licensed by Transitive that allows running PowerPC code on Intel hardware. There are 2 basic ways of constructing something like Rosetta, and I'll first show you how it's not done. In kernel mode, we have X and U sitting on top of the hardware, and libsystem sits right on top of the kernel interface. And on top of that, there are several libraries. Rosetta could use all the native i386 versions of these libraries, sit in the address space of the PowerPC application, and translate all its instructions on the fly, and interface the application to the library. A problem is that PowerPC is big endian, while Intel is little endian. So Rosetta would have to translate all the data that is passed between the emulated code and the native library. So it's not done like that, because the interface between an application and the hundreds of libraries that it might probably use is very broad. And Rosetta would have to know about all the data structures that are passed between these interfaces. Instead, it loads and translates the application and all the libraries that are needed, that are required by the application. It loads it down to the libsystem. So it only needs to do byte swapping between libsystem and the kernel interface, which consists of not more than a few hundred calls in total. So it's a lot easier to get right. The downside of this, of course, is it's slower. Like, for example, if a PowerPC application uses the QuickTime library, the movie decoder will run in a translated fashion, although it will be available natively on the system. You can make your own experiments and run the PowerPC version of a universal binary explicitly by running user libexec OAH translate, and you'll see it's slower. Talking about Intel and PowerPC, let's look at the different architectures NeXTSTEP or Mac OS X have been available for. Like I said, they started off as a 68K operating system, and it was ported to i386 and PA RISC and SPARC, and ported to PowerPC by Apple. And although i386 version has always existed, and it was actually released as a part of Darwin, it hasn't been part of a consumer product until 2006 with the introduction of the Intel Macs. So no i386 NeXTSTEP or Mac OS X was available between 1997 and 2006, just the open source Darwin pods, not a product. The Intel kernel of Mac OS X has 2 interesting features that distinguishes it from other operating systems. One of them is the split of virtual address space into the user and kernel part. On most other operating systems, like Linux, user mode occupies the lower 3 gig and kernel mode the top 1 gig. So when the kernel switches between tasks, it replaces the lower 3 gig with pages of another user. This is called the 3-1 switch.